In this first video for chapter 8, we're going to really set up the logic for the hypothesis tests, which are going to carry us through this whole chapter. And I'd like to begin by sharing with you again what features we're going to be using on our calculator. Back in chapter 7, we dealt with the t interval and the 1 proportion z interval in item numbers 8 and A in your calculator menu. For this chapter, we will be focusing on the corresponding hypothesis tests, the t-test and the 1 proportion z-test found in items 2 and 5 on your calculator's test menu. Now, as we mentioned previously, we're not going to be using any of these ones that I have crossed off in positions 1, 3, 7, or 9 on our calculator. That's kind of what we have decided as a math department here at VVC. Okay, let's continue straight into talking about what these hypotheses are. A hypothesis is a statement or a claim about the value of a population parameter. Now, there are two hypotheses. We have the null hypothesis, which we will write H subscript 0, and you will usually want to call it HO, but it's H0, and it is what we assume to be true unless proven false through the use of sample data. Think of it as innocent until proven guilty. We have the burden of proof to show that something is guilty, a person is guilty in a trial. Now, the alternate hypothesis is what we're trying to show, okay? What must be true if the null hypothesis is false. And we're going to have three types of alternate hypothesis. When they say this is the value, and we say, no, I disagree, we're saying you can be wrong in two ways. You can be either too high or too low. And we reject that claim in two ways, and that's what we call a two-tailed test. In a left-tailed test, we say, I think the value you are asserting is true is actually too high, and we think it should be lower instead, and therefore it will be a less than test, a left-tailed test. And if we think the value they are claiming is not high enough and that the true value of the parameter is higher, we're going to go with a right-tailed test. So in this first example, I'm telling you that a new car company claims that their car will average 35 miles per gallon for highway driving. Now, that HO, mu equals 35 miles per gallon, is their claim. Now, if we disagree with that claim, we're saying, no, I disagree, then we would use the inequality not equal to. Now, when we test a claim, we assume the null hypothesis is true, and we verify whether our sample mean lies within a certain number of standard deviations of the true mean mu. Okay, in other words, is X bar within perhaps 2 standard deviations to either side of the mu? And I say 2 standard deviations as a starting point. 2 standard deviations says, hey, I'm pretty much 95% confident it's within this middle range here. And only if it's outside of that range are we going to reject that claim. Okay, so basically we're saying if we take the other 4.5% and split it up amongst these two tails on the left and the right, we're saying it's got to be rather extreme. It's got to be a significant departure from the central value mu in order for us to say, hey, the finding isn't equal to what you're claiming. And I use that word significant properly in that context. Now, I've got this example we started the class with dealing with Raisin Bran. Okay, we wanted to argue that they're not giving us the 2 scoops of raisins per box, which we needed to quantify because that wasn't something we could actually sue against. And so we said, let's assume that they're claiming there's 300 raisins per box, and we think that they're gypping us raisins and they're giving us far less. Well, their claim, their null hypothesis would be that mu is equal to 300 raisins. We're giving you 300 raisins per box. And we are saying, no, I disagree. I think you're giving us less than 300 raisins. Now, I want you to notice that these inequalities are not opposites with each other. Anytime you write a null hypothesis, you use an equal to sign in that null hypothesis, even though technically the opposite of the less than would be a greater than or equal to. We understand that the null hypothesis really does have a greater than or equal to 300 raisins. When they say they're giving us 300 raisins, they mean we're giving you 300 or more and we're not gypping you. And the opposite would be less than. But we don't write that greater than or equal to symbol. We just write the equal to sign when we are writing a null hypothesis, always. Now, here's our first example, and British thermal units, BTUs, are probably not familiar to you unless you're looking closely at your gas bill for your apartment or home. And it says here, 1 year, the mean energy consumed per US household was 103.6 million BTUs. Okay, that was based on data, and that was for all US households. For that same year, 20 randomly selected households in the West had the following energy consumption, and they give us this data. Now, the West is being contrasted with the United States. Perhaps we're thinking, hey, in the West, it doesn't get as cold, we don't have these nor'easters, and we don't have to heat our houses as much, and therefore the energy consumption probably isn't the same as it is for the whole nation. Now, I've got some words underlined over here at the left and emboldened because this is how many hypothesis tests begin. They begin with the phrases, do the data provide sufficient evidence to conclude that whatever the alternate hypothesis is going to be? They're asking you a question. Do we have enough evidence to go with this alternate instead? That's language that you want to watch out for. And in this case, we're asking, do the data provide sufficient evidence that the mean energy consumption by Western household differed from that of all US households? Okay, usually in this question, they'll identify what the alternate hypothesis is going to be. You're looking for words like differed, exceeded, was less than, things like that that help you identify an inequality. And then they say, assume that the standard deviation of all the energy consumed for all Western households was 15 million BTUs. Now that is actually our value of S. It comes from Western households, and that's our sample. So that's a sample standard deviation. Now, in any hypothesis test, you begin with your null and your alternate hypothesis. And I'm going to write this for you in two different ways. The first way is we're going to assume the null hypothesis HO is that the mean in the West is equal to 103.6 million BTUs. It matches the US household mean. And then alternately, we're trying to show the mean in the West is not equal to, that comes from the word differed, the 103.6 million BTU. Now, when you write this, I like to put a meaningful subscript in because it helps me with the context of the problem. You can get a little bit lazy and just say, oh, null and alternate, mean equals, mean not equal to, and go that route. But it helps to have the units there as well as a subscript to help you lock in on your brain what you're actually talking about. Okay, notice I don't say HO equals, okay, I say mu equals. I have to have a parameter there that we're making a decision about. And remember, back in the beginning of the class, we said we start with statistics, X bar, to make a prediction about mu. These are claims about population parameters such as mu, and we use our sample values, our sample statistics, as evidence to reject the claim that they are asserting. And in this case, we're trying to show not equal to. Now, part B says, obtain a precise criterion for deciding whether or not to reject the null hypothesis in favor of the alternate. Okay, well, here's going to be what I'm going to suggest here. We're going to look at our sample mean and we're going to determine whether this X bar is within perhaps 2 standard deviations to either side of the claimed mean of 103.6. Now I said perhaps 2 standard deviations because we won't usually use this 2 number in general. We're going to use some other number because when you go with 2 standard deviations, that matches along with 95.44% confidence, and usually we don't want to be at 95.44. You remember the 68, 95, 99.7 rule? We want to go with a whole round number instead of a 95.44%. So we won't usually go with 2 standard deviations on the nose. Okay, so what am I asking you here? We're assuming that the mean is going to be around 103.6, and we're going to go plus or minus 2 standard deviations. But I took that standard deviation and divided by the square root of n because we're dealing with means and we're going to have samples of a given size, and that came from the central limit theorem that we learned in the previous chapter. Over here in the picture at the right, we're going to say, okay, right here in the middle, whoops, let me get my pen. Right here in the middle, that's where the 103.6 is. And we're just trying to say, hey, 2 standard deviations to the right or 2 to the left, that's going to be our boundary. We're going to let you have some leeway. But if it's beyond those marks with the not equal to, when I'm saying not equal to 103.6, back over in the null hypothesis, we're saying it can be wrong in 2 ways. Either it's much higher or it's much lower. It can go either way, being not equal to. So we're going to have what we call 2 rejection regions. And you can see that the rejection regions are what we've shaded in on the far left and in the far right. And then we have this critical value. If we go more than 2 standard deviations to the left or right, that's when we're going to say, enough is enough. But in the middle here, that'll be our non-rejection region. That'll be, yeah, we don't have enough information to say that the difference is significant. Okay, so let's apply this criterion of is X bar within 2 standard deviations. Let's find out what 2 standard deviations to either side of the mean is. So I took the mean, 103.6, there's my 2. My standard deviation in this sample was 15, and we took a sample of size 20. So there's my square root of 20. And then I actually did those values out of my calculator. I multiplied 2 times 15 divided by the square root of 20. And then I both added it and subtracted it from 103.6 to get this interval. Now, I'm not going to worry about being able to do that calculation myself manually because, quite honestly, we're going to be doing our hypothesis test in a slightly different way. I'm just trying to show you logically what's going on. So what we just established in this picture is the values of these dotted lines, okay? We have 96.9 on that left boundary and 110.3 on that right boundary. Then what we're doing is we're gonna look at our sample mean from our data, and we're gonna ask, is that going to be the test statistic that we're going to be looking at? Is it going to be in the central region, or will be off in those rejection regions on the far left and on the far right? So now what we're going to do is the following. Let's take a look at our data. I'm going to tell you from this data set, the mean in the West was 79.65 million BTUs, and with a standard deviation of 11.717. So I guess I actually need to go back here and change what I had said was X bar into sigma instead. I apologize there. I probably shouldn't have said all Western households. I just should have said all households. But there's our mean and standard deviation from the sample data. Now, let's go and standardize it. Remember how we're going to take a z-score here. X minus mu divided by, and instead of sigma that we learned back in chapter 3, it's sigma over root n. So I took my sample x bar minus that 103.6. How far away is that? But then let's find out how many adjusted standard deviations that is. So let's divide by these values there. And what we end up getting is, and let me move this, negative 9.14. Wow, that's more than 2 standard deviations below the mean. That's way off here in this rejection region off on the left. So that's going to be, whoa, strong evidence that says, the mean in the West is going to be different. So how am I going to word this? I'm going to say, since the sample mean is so far below the confidence interval that we had created up here in part C, and since the sample mean is 9.14 standard deviations below mu based on the z-score, we can be extremely confident in saying that the mean energy consumption in the West differs from the nation's mean of 103.6 million BTUs. Okay, this is meant to give you an idea of how a hypothesis test is going to work and the logic behind having a rejection region and a non-rejection region in the center there. We will not be physically drawing this picture and looking at this picture. We'll be doing it a different way when we get into the next video dealing with the actual hypothesis test. But this is really the heart of what's going on. The standard old-fashioned way, I'll call it the classical way of doing a hypothesis test, is to draw a picture and to draw these rejection regions, but there is a much easier way that we'll be doing using what we call p-values instead. Now let's continue on here. And as we've mentioned, there are 3 different types of problems. We have this not equal to pattern. With that not equal to pattern, we're going, I think you're wrong. I think instead of the mean being at this value, it's either higher or lower. This second one is a left tail test, and your alternate hypothesis will have a less than in it. That's what we just did with that raisin bran example. And a right tail test is going to have a greater than in its alternate hypothesis. Now, whenever we make a decision to either reject the null hypothesis or not, there's a chance we could be wrong. We could be making a mistake. So we're describing 2 possible types of error that we could make. And a type 1 error is where we reject HO when HO is actually true. In other words, we say, you're wrong. You're not giving us our 300 raisins of raisin brands. You're gypping us when, oops, they really are. We just had a bad sample. Get it? That was a mistake on our part. And a type 2 error is where we agree with the null hypothesis. We don't reject it when actually HO is false. We say, I wish I had enough evidence to really say that they were gypping us our raisins, but you know what, I don't feel comfortable with it. I'm going to just say, you know what, you're giving us the 300 raisins, and then oops, they really were giving us less raisins. Okay, that is a second type of error. Now you need to understand that these 2 types of errors, you need to be able to identify these 2 types of error in context and be able to word them for a particular problem or identify them in a particular problem. Now what we have here is in this table below is the same stuff I have in these sentences up above, but inside of a truth table. Okay, let's pretend we reject the null hypothesis. If the null hypothesis actually is false, that was a correct decision. But if the null hypothesis actually is true and we reject it, that's going to be a type 1 error. But if we fail to reject HO, okay, and HO is actually true, Okay, well, that was the right move. Okay, that was a correct decision. But if we failed to reject HO when HO was actually false, then that was another type of error, a type 2 error. So you can either memorize these error types through the use of these sentences right here, or some people prefer this logic table. They say the same thing, but in two different ways. Now, we mentioned these two error types, and the alpha that we've been dealing with in the past chapter is the probability of making a type 1 error. Okay, so as we've been drawing these pictures and we've been shading in these different regions, we've been saying, ooh, I'm going to reject. Here's my alpha down below. Here's my alpha up above. Or if we're splitting that alpha into two tails, we'd have alpha over 2 to the right and alpha over 2 to the left. That alpha is the probability of a type 1 error. Rejecting HO, that's the rejection region that I have just shaded in within these three patterns. Now, the type 2 error, we actually denote with beta, and the mathematics of beta is not even done on our graphing calculators, and it's not part of our intro class. So it's a good news. That's actually known as the power of a test, and we're not going to deal with that. But if you move on to a future math class involving statistics, you probably will. But I do want you to know that for a fixed sample size, the smaller the type 1 probability, the larger the type 2 error probability, and vice versa. I like to kind of liken that to using a clutch and a gas pedal in a manual car. Okay, you have to ease off the clutch when you put your gas down and ease off the gas when you're doing the clutch. And the two just kind of work. There's an ebb and flow relationship. If you are being so careful not to be wrong in suing for less raisins, then you're going to be more willing to accept their claim, even though it might be wrong. But if we're so cautious to not avoid being a type 2 error, then we lead ourselves into a type 1 error instead. Okay, this next example dealing with juveniles in public custody is a key example dealing with these type 1 and type 2 errors, and you will have a problem like it on your next test for sure, hands down. Okay, so know this inside and out. 10 years ago, the mean age of juveniles held in public custody was 16 years old. Statement. The ages of a random sample of juveniles currently being held in public custody are to be used to decide whether this year's mean age of all juveniles held in public custody is less than it was 10 years ago. So the null and alternate hypotheses are, and we assume in the null hypothesis, the mean is still 16 years old. That's how old they were 10 years ago. That's how old they are now. But we're trying to see if the mean age is less than it was 10 years ago. In other words, whether it's less than 16 years old. So there's our null and alternate hypothesis, where mu is this year's mean age. Okay, is this year's mean age under 16? Okay, explain what each of the following would mean in context. In other words, I don't want you to say type 1 error, reject HO when in fact HO is true. Yeah. What does rejecting HO mean? Well, it means that you are going to be claiming the mean age is less than 16. That's what H1 is, when it actually still is 16 years old. A type 2 error is going to be agreeing with HO. So you're going to say claiming the mean age is still 16 when it actually has decreased, when it actually is less than 16. Anytime you are describing an error, you have to have two parts. You have to say, this is what I went with, and it's wrong because it should have been this. That's why I say claiming this, claiming whatever we're going with, when it actually should have been this instead. A true good explanation of error not just says, oh, an error, putting my finger in a flame. Why was that an error? Well, because that can burn you. Okay, you need something that tells us why it's an error. Now, there are two types of correct decisions. Now, when I word a correct decision, I use the word correctly at the beginning. Correctly claiming the mean age is still 16, or correctly claiming the mean age has decreased. Okay, now by using the word correctly, I don't need to have two parts of a sentence, okay, because I'm saying this is what I went with, but oh, by the way, it was right because I used that adverb correctly. Okay, so two types of correct decisions. Now that is describing it in context. Now we go in the other direction as we continue reading. It says, now, suppose the results of carrying out the hypothesis test lead to rejection of the null hypothesis. In other words, that was our decision, reject HO. Reject the null hypothesis of 16 years old. That is, we're going with the conclusion that the mean age has decreased. It is under 16 years old. So that was our decision. Classify that conclusion by error type or as a correct decision if, in fact, this year's mean age mu of all juveniles being held in public custody is, and in part D, is 16 years old. We rejected the 16. We went with the less than. Oops, it was 16. That is a mistake. And because we rejected HO, that is a type 1 error. If we rejected HO and went with the less than, and in fact the age is less than, that was a correct decision. So I need you to be able to recognize and articulate what these different error types are, because that really is the heart and the beginning of what this chapter is going to be about.